Nathan told us that there are 4 ways that chefs use to control the viscosity. There are reductions, there's starch-based thickener, there's making an emulsion by adding fat, or using modernist thickeners, where small amounts of material, small amounts of a polymer are added to increase the viscosity by large amounts. In all cases, what we're doing is adding something to the fluid. In the case of reduction, we're reducing the amount of liquid, and what remains are particles or non-volatile solids. This increases the concentration of the solids in the liquid. In the case of starch, we're adding starch granules. In the case of fat or making an emulsion, we're adding drops of fat. And the drops of fat behave just like particles. In the case of the modernist thickeners, we're adding polymers, and they also have the effect of adding something to the fluid, and this is what increases the viscosity of the fluid. The simplest way to understand this is to think of particles in the fluid. Imagine particles in the fluid. When the fluid flows, the particles also flow, and they have to flow over one another in order for the whole suspension, the whole fluid to flow. The way they behave depends on the concentration of the particles in the fluid. It depends on the volume of the particles, or the volume that the particles occupy in the fluid. This is called volume fraction, or the volume fraction of particles in the fluid. We can calculate that easily. We calculate the volume of each of the particles, and we take the total number of particles times their individual volume and divide that by the total volume of the fluid. That gives us the volume fraction of the particles in the fluid. That's the important parameter that determines how the particles impact the viscosity of the fluid. That's the important parameter that tells you how the particles behave when they flow in the fluid, and how they resist the flow, or how they add to the resistance of the flow of the fluid. When there are very few particles in the fluid, or their volume fraction is very low, then they have almost no effect at all. When the fluid flows, the particles just flow with the fluid. There's no interference of one with another particle. The particles flow along and they don't see their neighbors. In that case, the viscosity of the fluid is just the viscosity of the fluid itself. The particles play no role whatsoever. However, when the volume fraction of the particles increases, then they become crowded. They interfere with each other. It's more difficult for the particles to flow over one another. And they collide with each other. They move on top of each other. They take much more volume, and the flow is restricted. In this case, the particles really impact the flow of the fluid and increase the viscosity of the fluid. However, for that to happen, the volume fraction of particles has to be quite high. It has to be sufficiently high that they can't easily flow over one another. This doesn't happen unless the volume fraction of the particles gets to be of the order of 50%, or half the volume of the fluid is occupied by the particles. When the volume fraction is so high, then the particles can't easily flow over one another, and this interference with the flow causes the viscosity to increase. Now we can understand in a very simple way why starch is so effective at increasing the viscosity. Remember that Nathan told us that you change the viscosity of a fluid by adding a lot of starch, but in his case, a lot of starch was only about 15%. Why does this happen? Well, the starch forms granules, and the granules are dissolved in the fluid. But two things happen when the granules are dissolved in the fluid. First, the starch granules expand. They absorb water and they get larger. As we show in this little cartoon, the volume gets larger, and so the volume fraction, the effective volume fraction of the starch granules, increases. And while you may start out with only 15% volume fraction, when they've expanded, then they can occupy a much larger volume fraction. So the water inside the starch granules doesn't flow. It flows with the granules themselves, and the effective volume fraction goes up, and therefore the viscosity goes up. The second way that starch can increase the viscosity of the fluid is that the granules stick together. In that case, they form these more tenuous structures, as we show here. The volume of these tenuous structures is the volume of the structures themselves plus all the water that they enclose, as shown by this circle. This increases the effective volume fraction of the particles. It allows them to occupy more volume because they pull the water along with them. This increase in volume fraction of the particles also leads to an increase in the viscosity of the fluid. And that's how you can greatly increase the viscosity of a fluid, even if you don't have essentially 50% of the volume. You have 50% of the volume fraction of particles because the particles occupy a much larger effective volume. Indeed, in all cases, in order to increase the viscosity of the fluid, you need to increase the volume fraction of the particles, or whatever it is in the fluid, up to about 50% or somewhat higher. It can be larger structures of the starch granules. It can be expanded starch granules. The same thing happens if you do a reduction. You reduce the amount of fluid and therefore increase the volume fraction of whatever is left over, be it solids or solids that are stuck together. But somehow you're increasing the volume fraction of the particles in the fluid. The same thing happens with an emulsion. There you're putting drops in the fluid. The drops have to occupy something like 50% of the volume of the fluid in order to get an increase in the viscosity. This can happen either by adding enough drops or by having the drops sticky and forming these larger tenuous structures in exactly the same way that the starch granules did.